Okay, welcome to the Chapter 2, Part 6 video. This is graphing rational functions. I mentioned this in class. Rational, we should always think of as fractions. So what are we going to learn about? We're going to review slash kind of look into rational functions. We're going to look at transformations of the reciprocal function, which we did a worksheet on. We're going to look at limits and asymptotes in a kind of a new way, in an additional new way. We're going to analyze the graph of rational functions, including looking at transformations on rational functions. And why is this important? Well, rational functions are used in calculus and in scientific applications, such as inverse proportions, when you have to divide something instead of something being equal to something multiplied. So for example, when we're looking at polynomials, when we add, subtract, or multiply polynomials, we end up with another polynomial. But when we divide polynomials, we end up with a rational function. So this is kind of the next step after polynomials, is to look into what happens when we divide by a polynomial. And the reciprocal function is an example of a rational function because you have a fraction where you have a variable in the denominator. So rational functions are fractions with variables, polynomial divided by polynomial. And that's actually what we're going to start with. Our definition of a rational function is if f and g are polynomials where g of x is not 0, we can never divide by 0, then any function given by the ratio f of x divided by g of x is a rational function. Okay, this is a different r of x than remainder. This is not the same as remainder. Okay, so the way that I like to think of rational functions in a one-word summary is rational is fraction. So I'll say this a lot. When we think of rational, we should always think of fraction. So I'd like you to give me one example in Edpuzzle of where else in math do we use the word or the title rational. Okay, so let's look at rational functions. So if I'm dividing by polynomials, we've already seen this when we were looking at domain. So let's go back and revisit. When we're finding the domain of a function, we look at the denominator cannot be 0, and we look at radicals cannot be negative. The radicand cannot be negative. So in this example, we'd like to find the domain of f, and we also want to take another look at limits. We're going to use limits to describe the behavior of the values of x that are not in its domain. So we're going to look at those asymptotes and say, well, what is x doing around those asymptotes? Because at the asymptote, x doesn't exist, but next to it, it does some interesting things. As we've noticed with our reciprocal functions, they actually tend toward either positive or negative infinity on either side of an asymptote, and they don't have to go opposite directions. We saw an example with 1 over x squared that they go both towards infinity, right? So in this function, what we need to do in order to graph this is find the asymptote and then look at the behavior around that asymptote. So let's start with the vertical asymptote. Vertical asymptote comes from the denominator equal to 0. So if we say x plus 2 equals 0, then x is negative 2. So we have a vertical asymptote at x equals negative 2. Let me try that again. Okay, there we go. X equals negative 2. There is our vertical asymptote, dotted because it's not part of the function. We've talked about that before, how the vertical asymptotes and the horizontal asymptotes are guides that give us an insight into the shape of the function, but they themselves are not part of the function. So that's our vertical asymptote. We can also have a horizontal asymptote, where we take the leading term of each of our numerator and denominator. So our numerator, our leading term is 2. Denominator, our leading term is x. Because 2 divided by x doesn't have a quotient, we know that that is purely a remainder. So we say y equals 0. So our horizontal asymptote is at y equals 0. Okay, so we found the asymptotes. Let's find the domain. Domain is all x values that can exist. Well, if we know kind of the guides for the function, then we know that x can be any value except for negative 2. So our domain is from negative infinity to negative 2, and then from negative 2 to infinity. Okay, and then we want to find its behavior. So in order to find its behavior, we need to plot some points. Notice that when x equals 0, I don't have an asymptote there. So that's a good place to start. So let's make an XY table. What happens when X is 0? Well, when X is 0, we get 2 divided by 2, which is 1. So we get the point 0, 1. That tells me that the first arm of my graph, or the right arm of my graph, is in quadrant 1. I'm just sketching. I'm not going to spend too long drawing this graph, but I do want to point out a couple things. It's going to go through that point that we found, and it's always getting closer to the asymptotes. So as it moves to the left of the point that we drew, as it moves to the left, it's going to get closer and closer to this asymptote at -2. And then as we move to the right, it's going to get closer and closer to this asymptote at y equals 0. So that's what asymptotic behavior is. The graph is kind of attracted to those asymptotes as it tends outwards towards the ends of those asymptotes. Okay, so we found the right arm. We need to find the left arm. So we need to test a number that is less than -2. I'm going to choose -3 just because that's the number that seems like it would be the easiest. So I chose -3. 2 divided by -3 plus 2. -3 plus 2 is -1. So that gives me -2. At -3, we're at -2. So that tells me that the left arm of our graph goes out and up and then out and down. And so we have our graph here. Now we should also be able to recognize this as the reciprocal function that has been transformed to the left by 2 with a vertical stretch of 2, right? So we can also recognize it that way. But when we're looking at rational functions in general, they won't always be as easy to identify as transformations of the reciprocal function, because we might end up with a polynomial in the numerator as well. So now we have a little bit of insight into that. The last thing that we want to do here is describe its end behavior. So the end behavior here, remember we were talking about the limits as x goes to positive and negative infinity for this type of function can be a number. It doesn't have to be infinity. So we can say the limit as x approaches infinity. As x gets really big, what is f of x doing? Well, as x gets really big, our f of x is getting closer and closer to 0. As x approaches negative infinity, the same thing is happening. So I'm just going to say that's the same thing that's happening as the limit as x approaches negative infinity of f of x. Okay, I want to introduce a new type of limit here. So we saw polynomial end behavior. So as x approaches plus or minus infinity for polynomials is going to be, the end behavior is that the polynomial ends are going up or down. For rational functions, including the reciprocal function, the polynomial behavior could be approaching a number. But then we have this end behavior that's happening kind of in the middle of the graph as well. We have arrows that are pointing off the graph within the middle of our x values. And so we can also write those as limits. What we can do if we're looking at the right arm of the graph, and I'm going to highlight it in red here, as x gets closer and closer to -2 from the positive side, so we're approaching -2, this is my positive side, this is my negative side. So as we approach -2 from the positive side, my graph is going up to infinity. So we can write that as a limit, and we would say the limit as x approaches -2 from the right, the little plus, meaning from the positive side, of f of x equals infinity. So the limit as x gets closer to -2 from the right-hand side is that our y value is going up. Very similar to the polynomial end behavior, but it's happening not at the ends of our graph now, but in the middle of the graph. Okay, and then the other type of limit we can do is the limit as x approaches -2, not from the right side, but from the left side. So a little negative exponent. It's almost like an exponent, right? It's raised above the 2 of f of x equals -infinity. Okay, So that means that as my function approaches -2 from the left-hand side, my x values are getting closer and closer to -2. My y values are going down. We'll see more examples of these types of limits. Okay, let's look at our next, oh, well, the limits that we just talked about. I forgot that I added a slide in here. So let's just write them again. So the limit as x approached infinity, we had our asymptotes, and I'm doing a really rough sketch just to look at these limits again. So the limit as x approached infinity was going to 0. The limit as x approaches -infinity was also going to 0. The limit as x approaches -2 from the positive side, that's this way, is going to infinity. And as x approaches -2 from the negative direction, so that's coming in this way, is going to -infinity. Okay, those are the same limits that we just did on the previous slide. All right. So let's look at a couple more examples of rational functions, and we're going to relate these to that worksheet that we did with the transformations from the reciprocal function. So part A, we're looking at, we have a function h of x equals -2 divided by x plus 3. Okay, so right away, what I notice is that we've got an x in the denominator. That's what makes it a transformation from the reciprocal function. Looking at these transformations, we know that the x plus 3 goes left 3. 2 in the numerator, that's multiplying by 2. So that's a vertical stretch by 2. And then the negative is out front of the fraction, not attached to the x. So that is a vertical reflection. If I reflect vertically, that would be over the x-axis reflection. Okay, so if we sketch this, we've moved to the left by 3. We have not moved up or down. So that means our horizontal asymptote should still be at 0. We can double check that by dividing. 2 divided by x has no quotient. It's all remainder. So that confirms our horizontal asymptote at 0. Y equals 0. X equals -3. Okay, it did reflect. So that means that my right arm is below the axis and my left arm is above the axis. So how can we write our limits? Well, let's start with the limit as x approaches infinity. So that's when the graph is going off to the right side. That's approaching infinity. What is happening with my y value? Well, as x approaches infinity, the function, the y value, is getting closer and closer to the x-axis. So that is 0. Let's see what's happening on the left side as x approaches -infinity. As x goes off to the left of the screen, my y value is getting closer and closer and closer to that x-axis. So again, that is 0. And then we want to look at the middle behavior, or the asymptotic behavior. And so we have the limit as x approaches the asymptote. What is the value of our asymptote here? We're looking at an x value of -3. So in here, we're going to fill in -3. And so as x approaches -3, my pen doesn't want to do the negative signs again. As x approaches -3 from the positive direction first, so from the positive direction, that's this way, what's happening to my y values? My y values are decreasing to -infinity. As x approaches -3 from the negative direction, my y values are increasing to infinity. Okay, let's just make sure we hit all of these points. We described the transformations, good. We identified the asymptotes, we used the limits to describe their behavior, and we sketched the graph of the function, good. Okay, I want you to try part B, okay, doing those same steps that we just looked at, the transformations, sketching and looking at the limits, and then we'll go through it together. Okay, so first thing I'm going to look at is the transformations. Now remember, when we did the worksheet, sometimes it's easier to tell the transformations based off the asymptotes. So our vertical asymptote is still the same, left 3, right? Our denominator is still the same. The difference here will be the horizontal asymptote, because to find our horizontal asymptote, we set y equal to the leading term of the numerator divided by the leading term of the denominator, 2x over x, which gives us 2. So there is our horizontal asymptote at y equals 2, and our vertical asymptote at x equals -3. So we move to the left by 3, up by 2, and we also have that leading coefficient of 2. So that's a vertical stretch by 2 because of our leading coefficient there. Okay, so to sketch this, I know it has not reflected. So I've got my arms are going up on the right and down on the left. And then we want to find our limits. So first limit, as x goes off to infinity, what are we approaching? Well, as x goes to the infinity, our y value is getting closer to our horizontal asymptote, which is not 0 this time, but 2. Same thing as our x goes off to negative infinity, our y value approaches our horizontal asymptote, which is 2. This time we're approaching our vertical asymptote at -3 from the right, and we're going up to infinity. And when we approach our vertical asymptote from the left, we're dropping down to negative infinity. So really, when we're looking at the limits, we're looking at where are those arrows pointing. When we draw our graph, we draw the arrows at the end of our each kind of arm of the graph. And so the limits are telling us where are those arrows pointing. Okay, let's take a look at our next slide. So graphing rational functions, this is actually the only slide of this, not one of 2. Graph of a rational function. So there's 4 properties that we've been looking at for the graph of a rational function, which is whenever we take a polynomial divided by another polynomial, so we have our numerator and our denominator here, we can have the end behavior asymptote or the horizontal asymptote. However, if the numerator has a degree higher than the denominator, remember I said we were going to talk about that case later, well, it's later. So what happens if our numerator is larger than the denominator is that we end up with what's called an oblique asymptote. So let me give you an example. If I have something like 3x cubed divided by x squared, okay, and that's my rational function, because the numerator is a higher degree, when I simplify that, it becomes 3x. Well, if I graph 3x, that's not a horizontal line. That is a line with a slope, right? A slope of non-zero. And so we call it oblique. Oblique means sideways, or like your obliques are part of your abs, are the abs on the side, right? So obliques are on the side. So an oblique asymptote is not horizontal, it's not vertical, it's kind of sideways, okay? It's at an angle. And so when we're graphing rational functions where the numerator has a higher degree than the denominator, our asymptotes are not necessarily going to be vertical and horizontal. If we have an oblique asymptote, then we do not have a horizontal asymptote. Okay, so you find an oblique asymptote the exact same way that we found a horizontal asymptote, which is polynomial division. Okay, the vertical asymptotes still come from the denominator. We set the denominator equal to 0. And remember, if we simplify our rational function first and we have terms that cancel out, or factors rather that cancel out, those are removable. So those are not asymptotes. So that's what this last part means. If they're not removable discontinuities, meaning when we simplified the fraction, we didn't have anything that could cancel out. The same thing goes for x-intercepts. The zeros of the numerator that didn't cancel out, those are the x-intercepts, because if it did cancel out, then it is a removable discontinuity. Okay, and then lastly, we have our y-intercept, which is also called the initial value, and that's calculated by f of 0. Now, it's not always defined. If x cannot equal 0, then obviously we won't have a y-intercept because that will be a vertical asymptote, right? So if I have a vertical asymptote on the y-axis, then I won't have a y-intercept. I won't have what we call an initial value. So that only happens when x is defined for 0. Okay, so all of these properties we've talked about before. The only new thing on this slide is that oblique asymptote. Let's take a look at an example. So we want to find the asymptotes, and we also want to find the intercepts, and then we're going to try and sketch it. So we're given this function. Luckily for us, it's already factored, right? If it's not already factored, the last section where we looked at rational zeros and in factoring polynomials would help us factor this. So finding the asymptotes. First thing I'm going to do is I'm going to say, does anything reduce? No removable discontinuities. And then we're going to look at vertical asymptotes, which is the denominator, x plus 1 equals 0. So x equals -1, and x plus 5 equals 0. So x equals -5. Now these are our restrictions in the domain. So from here, I can also say that the domain is all real numbers from -infinity up till my smaller one is -5, picking back up at -5, going all the way to -1, and then picking up at -1 and going all the way to infinity. Okay, so from the vertical asymptotes, we also find our domain. Next, let's see if we can find our horizontal asymptote or oblique asymptote. So to do that, we have to divide, which means we need our leading term. So we have 2 times x times x. So that's y equals 2x squared divided by x times x gives me x squared. This gives me y equals 2 as a horizontal asymptote. If the degrees were different, then we might end up with an oblique asymptote. If the degree of the numerator is bigger, then when I simplify, I might have an x in my quotient, and that's when we get an oblique asymptote. Okay, and then we want our intercepts. So let's find our x-intercepts. For that, we set the numerator equal to 0, 2 equals 0, that never happens. So that's not going to give us a 0. X plus 3 equals 0 when x is -3. X minus 3 equals 0 when x is 3. And lastly, we'll find our y-intercepts, which is f of 0. So we have 2 times 0 plus 3 times 0 minus, 3, divided by 0 plus 1 times 0 plus 5. 2 times 3 is 6, times 3 again is -18, divided by 5 times 1 is 5. So our y-intercept is approximately -3. Okay, so here's my y-axis and my x-axis. And let's start by plotting our asymptotes. So our vertical asymptotes are at -1 and -5. And then we have a horizontal asymptote at y equals 2. So there's 2, there's -1 and -5. And then we can do our zeros and our y-intercept next. So our zeros at -3, somewhere over here, and +3. And our y-intercept is at -3-ish. Okay, so I know that my right side is going to do something like this because it's blocked in by the asymptotes. Okay, my right side, or the middle piece rather, is also blocked in by asymptotes, but I know that it only crosses the x-axis once. So remember I said there's one case that we can cross a horizontal asymptote, and that is for the case of a 0. So a 0 of multiplicity 1 is stronger than a horizontal asymptote. It's not going to bounce back just because of that asymptote. The asymptote will give way because of the 0. Okay, and then our last piece, the leftmost piece of the graph, we should test a point. So let's try -6. F of -6. 2 times, I'm going to do some mental math. So -6 plus 3 is -3. -6 minus 3 is -9. Divided by -6 plus 1 is -5. -6 plus 5 is 1. Okay, so this is going to be -27 times 2 is -54. Divided by -5 is approximately +11. Okay, that's way above 2. So we know that that arm is above our horizontal asymptote. Okay, so this is a sketch of our graph. We can talk about limits. The limit as x goes to infinity in this case will be 2. The limit as x approaches infinity of f of x is 2. We know that the limit as x approaches negative infinity of f of x also equals 2. I'm just going to draw in the other limits. So we have the limit as x approaches -1 from the right side. From the right side is negative infinity. Whoops, I forgot my f of x. Okay, from the negative side is positive infinity. And then we can say the limit as x approaches -5. From the left side, we'll do the left side first for fun, of f of x equals positive infinity. And from the right side equals negative infinity. Okay, this question didn't ask us for that, but just as a quick review of those limits. Okay, let's take a look at our next example. So again, we want to find the asymptotes, intercepts, and sketch the graph of this function. Okay, now this function is a little bit more straightforward than the last one because the degree of the numerator is smaller than the degree of the denominator, which the only thing that does is it changes our horizontal asymptote. Okay, I'd like you to try this one and then we'll go over it together. Okay, so I'm going to choose to do my asymptotes first. So I notice if I look at my factors, none of them cancel out. There's nothing removable. So I'll do my vertical asymptotes first. From the first factor, we get x equals 2. From the second factor, we get x equals -3. For my horizontal asymptote, I take numerator y equals x divided by the denominator gives me an x squared, which is 0 because it has only a remainder. Y equals 0. And then we'll find x-intercepts next. X minus 1 equals 0, so then x equals 1. We'll find the y-intercept next. That is the initial value. So that's going to be -1 divided by -2 times 3, which gives us 1/6. Okay, so those are the asymptotes and the intercepts, and then we'll sketch a graph. Starting with my vertical asymptotes at 2 and -3. Horizontal asymptote at 0. I do it a little bit off of the x-axis just so I can see it. X-intercept at 1. Our asymptote was at 2, so the x-intercept is between the y-axis and the asymptote. And a y-intercept is +1/6, so that's going to be above our horizontal asymptote. So that shows me the middle piece should go like this. And then I need to find the outside pieces. So I'm going to try a number that is bigger than 2 and a number that is less than -3. So let's try f of 3. 3 minus 1 is 2. 3 minus 2 is 1. 3 plus 3 is 6. So that is 1/3, which is positive. It's above my horizontal asymptote. And then we'll try f of -4. -4 minus 1 is -5. Negative 4 minus 2 is negative 6. Negative 4 plus 3 is negative 1. So that is 5/6, again, positive. So it goes above our horizontal axis. Oh, no. 6 and 1 makes that positive, so this is negative. So that goes below the horizontal asymptote. That looks better. Okay, now they could have, there was nothing wrong with having the left side of my graph above the asymptote. That could absolutely happen. I just recognized that that's not the answer I got before. So that's how I recognized that I had made a mistake with my negatives. Okay, how you can check these, you can always check it in your calculator, but just keep in mind, the more you rely on your calculator, the longer it's going to take to do each of these problems, the more tedious it's going to be, the harder it's going to be to apply them in the future. Okay, so try to use your calculator as little as possible, but absolutely you can use it to check your answers. I would caution you when typing these functions into your calculator, make sure to put an extra set of parentheses around the denominators. So if I'm typing this into my calculator, I would do y1 equals x minus 1 with parentheses divided by parenthesis, x minus 2 times x plus 3. So the reason we have to have those double parentheses is otherwise your calculator is only going to divide the first two and it'll multiply by the last one unless you group your denominator together. Okay, that's the last example for this. I'm just going to leave you with the properties. Ooh, let me clear those. The properties of the reciprocal function. Now, we've already talked about all of these properties throughout the first and second chapter so far. But if you wanted to go through and write them all in one place, maybe on that chart, or if you have somewhere in your notebook that you're keeping track of function properties or something like that, this is just a slide that summarizes the properties for the reciprocal function that we've talked about.